Welcome back to Calculus. In section 3.10, we're going to look at some linear approximations and differentials. This is really important, cool stuff where we learn some methods for approximating solutions to problems. It's often very useful and practical to be able to do that. So in this section, I want to tell you what the linearization of a function is. It's just the tangent line of it, but we're going to look at it carefully and how we're going to use that linearization to make estimates of the function values. So that's kind of the key application right there, making estimates of those function values. All right. I'm going to tell you something about something called the differential, the differential of a function and how it's used to estimate changes in the function. All right, so that's kind of a second topic and its main application. And then we're going to be making estimates. So we're going to talk about errors in those estimates, kind of more important quantity about relative error, and then just kind of expressing that either as a decimal or percent. All right, so that's our objectives. So let's get going. I've got kind of a busy slide here, but it's no new big information. We're talking about a differentiable function, and we've talked before that if you have a differentiable function, then you zoom in around a point on that function, it becomes difficult to distinguish the function from its tangent line. Yeah. So another way to say that is that the function is closely approximated by its tangent line, as long as you're staying near the point of tangency. You stay near that point of tangency, and your line and curve are hard to tell apart. Okay, that's the big idea. So we can use the tangent line to make a good approximation of the function. Yeah, I'm going to find the tangent line with just the good old point slope formula over here. I've got the point slope formula written down the way you'd see it kind of in an algebra book, and the point that I'm using is the a comma f of a. Yeah, so that's what I'm putting in for y0 and x0, and this formula is f of a and a. What's the slope? Well, the slope is the derivative. Yeah, if you're taking the derivative and you're plugging it into f of x, you get f prime of a. So the slope in this thing is there. That's my m in that formula. So I'm just writing the tangent line down using the point slope formula. And if I do a little bit of algebra, I'll just scroll up and reveal all this. I did a little bit of algebra here and then wrote it nicely in a box. And I'm calling that the linearization of the function. That's its full name, the linearization of f at a. And you have to have those two pieces of information. You have to know the function f, and you have to know the point a, and then the linearization of it is just this tangent line. If I'm writing it in function notation, its function name is L for linearization, and it's the equation of the tangent line. And our primary application of it, again, I'll say it over and over and over again, is that for points that are nearby a, that linearization is a good approximation for the function itself. So if f of x is some answer to a math problem that we're interested in, it's easier often to compute L of x, and L of x would be very close to that answer. So that's kind of the kind of practical side of our business here. All right, let's look at an example. So I said you need a function and a point, so here I've got one. So f of x is the square root of x plus 3, and I want to find the linearization. So I want to find the equation of the tangent line. So we need the point. Going to write this out with you. What's the point? Well, we're doing this at a equals 1, so the y-coordinate is dictated by the function, f of 1. So we got to do a little bit of arithmetic here. F of 1 is the square root of 1 plus 3. So our point that we're talking about is the point 1 comma 2. So when we go to write the equation of our line, that's the point we're going to use. Now we need the slope. Yeah, the slope's the derivative. You have to take the derivative of the function first. I think it's most useful to look at the derivative over here in this square root form for differentiation purposes. You can see it's a chain rule problem. The outside function's derivative of a square root is 1/2 times the minus 1/2 power. The inside function there is x plus 3. That's derivative is 1. So, and I'm not going to simplify that. I want to know the slope when x is 1. That's where I'm taking this point of tangency. That's my a. So I don't need to simplify that to do that. I can put in 1. The minus 1/2 power of a half is also a half. So the slope is a quarter. So now we are in business, right? We have what we need. We need a point and a slope to write the equation of a line. Let's do it. So we got y minus 2 is equal to a quarter times x minus 1 with our given point. Yeah, because our y coordinates here is 2 The x-coordinate goes right there in the formula. That was 1. And finally, the slope. Slope was 1/4. Came from our derivative. Cool. We want the linearization, so I'm going to write this as a function. L of x, I'm going to add 2 to both sides of this thing. 2, and I'm going to simplify it, I think, a little bit here. So what would we have? 1/4 x minus 1/4. Yeah. And then we have to subtract 1/4 from 2. So what would that be? 2 is 8/4. So that's 7/4 plus 1/4 x. There's our linearization. Nice. Sorry, it's a little messy and slanted over there, but that's what the question asks for. Find the linearization of this function at a equals 1. It is the line 7/4 plus 1/4 x. It's written kind of backwards in the usual form. You're used to writing it mx plus b. I've written it b plus mx. Cool. Let's see what this thing does. Let's use it to estimate the square root of 5. We were talking about the function square root of x plus 3. Well, 5 is 2 plus 3, so we're going to use L of 2. Does that make sense? L of 2 it would be very close to f of 2. And f of 2 is 2 plus 3, or square root of 5. Yeah, square root of 2 plus 3 is square root of 5. Right, and L of 2, well, we're just going to plug it in. L of 2, sorry, I didn't mean to write approximately equal here. I'm just going to write L of 2 equals 7/4 plus 2 over 1/4. And that's 9 over 1/4. Or if you like, as a decimal, 2.25. So our estimate for the square root of 5, this is what I was trying to write over there. Square root of 5 is approximately L of 2. It's about 2, it's 2.25. Okay. And if you picked other numbers nearby 1, 2 isn't actually very close to 1, but nearby 1, these estimates won't be poor. I'm not saying very precise things about that here. I brought a table, though, where I can just sort of show you. We just computed this row in this table. We just took the value x equal to 2 and got that 2 1/4. There you can see the actual value of the square root of 5. Well, actual value, at least as many decimals is printed right there. Yeah, so you can choose other x values. I would pause for a second if it's not clear what we're talking about, because you got to remember this is the function x plus 3. So these numbers over here in the left-hand column are the square root of x when you add 3 to it. Yeah, so that's why. Okay, good. Picture on the left sort of depicts what we were doing. If you think of it to scale, where would our x equals 2 be? It would be somewhere in there. So we were estimating the y coordinate on that blue curve, that is the square root of 5, with the y coordinate on the tangent line. That was 7/4 plus 2/4. Yeah, so that's what we were doing geometrically. Cool. All right, let's keep going. Another busy slide here. This is just a definition slide, if you like. I want to tell you about this thing called the differential. So if you're given a function, y equals f of x, then its differential, by definition, dy is how we'll pronounce it, is the derivative f prime of x times dx. And in that expression, both x and dx you think of as an independent variable. So the differential is a function of 2 variables. One variable is x, and it gets plugged into the derivative, whatever it is. And there's a new variable, this thing called dx. And they're completely independent in the sense that one of their values doesn't have any effect on the other. You choose them independently. Okay? I've done out a couple of computations here to keep the video short. You should stop it and verify them. I didn't have any way of kind of revealing them or warning you, but just verify. But let's just look at them as we go. If you take y equal to be the sine of x, then it's differential dy. It's this thing that I'm calling the differential. It's the derivative, that's cosine, times this new variable dx. Okay, you can check it out with the chain rule. If y is this function of t, that's its differential. And notice that I wrote dt. You always do that, whatever the input variable name is. Okay, so if it's y, if it's t, if it's x, if it's w, it's z, the differential ends in So it's d output derivative d input. Cool. So what in the heck do we do with these things? Another busy slide. Let's kind of try to talk through this one. It's super busy. So usual picture though, just looking at a curve and its tangent line. Tangent at this point, P, okay? Not going to call the input variable. I want to think of it as a variable, so I'm calling it X. But then I'm looking at a nearby point, so I'm changing X by a little bit, delta X. And the nearby point is called Q. It's not marked. I could mark it a little bit there if you want. There's Q. It's the point on the curve that when you change X. And then this other point R, the point that corresponds on the tangent line. Okay. And then a new variable. I know the notation's getting a little heavy, but it's kind of fun. A new variable, delta Y. That's the change in the function value. All right. So you can see it in the picture there. He's got it actually drawn in blue. I should have done the same. But delta Y, it's how much Y changes when you change X along the curve, along the function Y equals f of X. Okay, that's what Y means. So you can also write that delta F. If you see me writing that, I mean the same thing. Y is equal to f of X. So delta F, delta Y, it's delta output. It's the change in the function's output. Okay, cool. All right, we've already talked about the slope of that tangent line is f prime of X. So this differential, this thing that we were just talking about, dy, this f prime of X dx, if we just give that independent variable dx the value delta X, yeah, I said it was an independent variable, then the differential in that case is the slope of that, it's the change along that tangent line. Because if you have a line with slope f prime of X, and you change X by delta X, well, you multiply the change in X by the slope to get the change in a line. So that's what the differential represents. It's how much the function changes along the tangent line. Yeah, so that's sort of its importance geometrically. So what does all that mean? Well, if these two things, remember, we've just set dx and delta x equal to each other. If those two things are both small, then this differential is a very good approximation for the change in the function. All right, and so we're going to use this differential to estimate the change in the function because it's typically a little bit easier to compute. So this is kind of the good news. The differential dy estimates the change delta y in the case that dx is equal to delta x, and in particular when they're small, the estimate gets good. So you can kind of imagine in this picture, imagine if this variable delta x could get smaller, that is keep x where it is, but imagine this vertical line moving to the left in the picture. Delta x is getting smaller. So I can't draw the vertical line, but I could draw you like where the point is. And every time you do that, delta x is getting smaller. And the smaller and smaller delta x is, the better and better that approximation will be, because this line and this line will be getting closer and closer to the same. Right, their difference is getting small. Cool. Okay. Let's look at some examples. Examples. You might have to pause, go back, look at that, have your book out. Let's look at this cube root function. It's cube root of x. And I want to estimate its change. See, I said earlier, I mean the change in y, change in f, as x changes from the number 27 to the number 29. I want to use differentials to estimate that, okay? Okay, so we should compute the differential, df. If you like, dy, but then I got to go up here and say, okay, well, by y, I mean f of x. So I crowded it in there. And what do? I take the derivative as usual, 1/3 x to the minus 2/3 by the power rule, and multiply by this new variable dx. It's something I just have to remember to do. It's part of the definition. Dx is the second variable. The differential is a two-variable expression, x and this new variable dx. Cool. All right, so that's the differential, right? And then, well, what's our dx? We said dx was going to be the change in x. Well, what do I mean by the change in x? Well, it's changing from 27 to 29. So it's 2. The change in x is 2. So we're going to estimate by letting x be 27, the place we're changing from, and we're going to use dx to be 2. So if we have that information, we can write down our differential. Yeah, it's 1/3. Going to let x be 27 and dx be 2. All right, and you can, I think, get your calculator. I'm not going to use a ton of room to do it, but the cube root of 27 is 3. You square that, and that's 9, but the exponent's negative, so that 9 is downstairs, times 1/3, so the denominator of this fraction will be 27, and the numerator is going to be 2. So our differential is 2 27ths, all right? So that's going to be our estimate for approximately how much the function changes if you change x from 27 to 29. All right, so that's how I can use differentials to do that. And maybe if you want, why would you ever want to do that? Well, this differential, it's an estimate for the change in the function, right? So maybe you, like me, know that the cube root of the cube root of 27, we already said this, is equal to 3. The cube root of 27 is equal to 3. But what about the cube root of 29? Well, we just computed the differential for the cube root function, yeah, the f of x. So this thing should be approximately, not exactly equal to the cube root of 27, plus this differential, plus this change in f, yeah, because if you take the function value and add to something that's about the change of f, then you should get an approximation for it. And we said that was 2 27ths. 3 would be 81 27ths, so I think that's 83 27ths. And I've got a handheld calculator here. I don't want to write a bunch of decimal places here, so I'm going to round to maybe the nearest hundredth, like a 3.07. You can look at some more. It's for 407 if I tried to write it out in here. That's how many decimal places my calculator showed me for 83 over 27. All right, so that's my estimate for the square root of 29, and I did it using this differential. Okay, so I kind of added something on the end of the problem there, but that's how we do this stuff. This calculation went pretty smoothly. I can estimate something like the cube root of 29 with this fraction, yeah, which I could do this with division if I didn't have my calculator. I could do it with long division. So that's the whole point, is the differential is easier to calculate than the expression directly. Nice. What if I wanted to change it around? What if I wanted to say, let's say that we change from 27 down to 25? What's that going to do? Everything about our derivative calculation will be the same. We'll use the exact same differential. Yeah, so we don't have to recreate that. We can just bring it down. We're also going to be using x equals 27. That's not going to change. That's not going to change. But this time our delta x, we have to subtract in the right order. We're still changing from 27. So it's 25 minus 27. It's -2. That's the difference. Yeah. So this time, if we compute our differential df, the calculation is going to go exactly the same, but we're going to have a minus sign. It's going to be -2 over 27. It's going to be -2 over 27. So if we were going to say, for example, estimate the cube root of 25, well, we could say that's approximately the cube root of 27 plus the differential, but in this case, we're going to have to subtract those 2 27ths. So that's going to give us this 79, I think, over 27. Or what my calculator says is that's about 2.93 Again, I'm lazy and just going to write 3 decimal places. So that's my estimate for the cube root of 29. It seems reasonable based above. It's slightly smaller, should be. Cool. All right. So there's that. What was the point of that example? Let me summarize. I was showing you what I mean by computing a differential. And then this bottom part was using it to estimate some function value, estimate the change in a function, and then yes, using that change to estimate some overall change. Nice. Let's do one more. This video is getting a little long, but let's try to make through one more. So kind of an application problem. So let's suppose for fun that we make circular discs, and they're supposed to have a radius of 20 centimeters. I'll just kind of highlight the information we're going to use as I talk. But when we make them, our machine, maybe it's defective or something, I don't know, but the radius can be off by as much as a centimeter high or low. So they might be 21 centimeter, they might be down all the way to 19, okay? And I want to use differentials to estimate the error in the area in the disks. So in other words, how much could the area vary, right? Well, what's our area supposed to be? The area of a circle, you remember, is pi times the square of its radius. So for our circle over here, we would take pi times 20 squared, yeah, or 400 pi. So our circle has area 400 pi. So I'm talking about what's the change in that? Yeah, the error in the area of the disks is the change in A, and I want to estimate that with differentials. So I'm just going to write dA. All right, that was the principle that I was talking about above, is that you want to estimate the change in some function. Well, let's do it with its differential. And I'm not calling it dy here. I'm just calling it, the output variable. And what's dA? Well, take the derivative. 2 pi r is the derivative of pi r squared, right? I'm differentiating with respect to r. I'm going to put that note information right there. That's my independent variable, dr. All right, so that's my differential. And I'm going to calculate that thing because, again, I'm going to write it again. This thing estimates the change in A. It's approximately equal to the quantity that I'm trying to talk about. So now I got to just say, well, what am I plugging in? Well, R is 20. What's dr? That's our information right here, plus or minus 1 centimeter. All right, so let's do it. 2 pi, I'm going to put in 20. And then I can write plus or minus. I mean, you could just write that at the end too. It's kind of a hassle to keep writing plus or minus everywhere. And so if you multiply that out, well, again, plus or minus, what, 2 times 40 pi units squared. I should put in my units here. These things are square centimeters. It's change in area. And as a decimal, can we call that about, I don't know, to the nearest whole number is a little sloppy, I guess, but it's 125 points. Should I write 664? That's what my calculator is displaying. Again, centimeter squares, pretty large. Pretty large. All right, but that answers the question. What's the maximum error? Well, the error could be plus or minus that number, 125, 126 almost square centimeters. So quite a little bit of area. Yeah. Good. Okay. So this is a good opportunity. We've covered most of what the learning objectives are in the lecture, but we still have to talk about. This is the error. So the error in a problem like this. Oops. Pardon me. Having a little malfunction there. The error in this problem was the change in the area. In general, it's the change in the function that you're considering. Yeah, that's this number that we just calculated right here, the 125. It's our error. Plus or minus just means where we could miss high or low. So you can also just say the error is 125 because it's always understood to be that you could miss high or low. Okay, but often a more interesting quantity than error is something called relative error. So you remember back at the beginning of the video on the objectives, we were going to talk about relative error. Relative error is the error you make compared to the size. Yeah. So in this particular example, it should be our plus or minus, I'm not going to write it, 40 pi square centimeters over the total area, which was 400 pi square centimeters. Yeah. So this is unitless. The relative error doesn't have units because you're taking the same units in the numerator and the denominator. So if you reduce that fraction, well, you get a tenth, yeah? You get a tenth. So the relative error here is a tenth. So it's actually not big. If you were surprised at the size of this number for just a small change in the radius, it's not insignificant, but it only changes the area by about a tenth. Or this is the last vocab word, percent error. The percent error, you just express this as a percentage. Yeah, so you'd say 10%. 0.1 is 10%. If you express the relative error as a percentage, then people call that the percent error. So we've talked about error, relative error, and percent error. Cool. So I've got just a summary down here to end with. If you take some function, and you're thinking of it in some application if you want to, but let's just call a change in its input the error. All right, so I'm just going to say that that's the error in the input. Then by the error in the function, I mean the output, and that's always approximated by the differential, which I'll just remind you is the derivative times this independent variable dx. That's the change in x. That's the error. The relative error is that output compared to the total, approximated by the differential. That's the part we compute. And if you want to write that as a percent, then it's called the percentage error. Cool. All right. Thanks for listening.